Hey YouTube, Olympiad Maths here, and today we're going to be looking at this problem from USAMO 2000 and problem 1, and it says, call a function very convex if f of x plus f of y over 2 is at least f of x plus y over 2 plus the absolute value of x minus y holds for all real numbers x and y. Prove that no very convex function exists. So we can recall that Jensen's inequality tells us f of x plus f of y over 2 is at least f of x plus y over 2. And this holds for all real numbers x and y for a convex function. So this tells us that we need to use the absolute value of x minus y part of the inequality, as this is the difference between a convex and a quote-unquote very convex function. Now Jensen's is not completely necessary. One can still build this intuition from just trying out different functions, for example, f of x being x squared. One can figure out that the absolute value of x minus y is the part that we need to focus on, although it is harder if you do not know Jensen's inequality. But Jensen's inequality is pretty much strictly just for building intuition. So we will want to chain together multiple copies of this inequality and get a contradiction, since this will allow us to add together a lot of the absolute values and artificially create a large number on the right hand side, which is the part that's supposed to be smaller. Note that in the inequality we have f of x, f of y terms on one side, and the other side has an f of x plus y over 2 term. So to chain together the inequalities, we will need something like what is shown. So what I did is I worked backwards. So for example, we start with f of 2 on the right side of the inequality. How do I get to f of 2? Well, I can start from, let's say, f of 1 and f of 3. And where do I get f of 1 and f of 3? Say I can go with f of 0 plus f of 4 and 2 copies of f of 2. In doing so, I will get an inequality such that I have f of 0 and f of 4 on one side, and I have an f of 2 somewhere on the other side. Now, the coefficients in front of the terms doesn't really matter. I just need these two function terms to be present so that I can compare this with the original inequality. So let's expand on this idea. So if we're strictly just copying the 0, 2, 4, which leads to the 1, 3, which leads to the 2, we have something like this. We have f of 2 plus f of 4 over 2 is at least f of 3 plus 2, f of 0 plus f of 2 over 2 is at least f of 1 plus 2, and f of 1 plus f of 3 over 2 is at least f of 2 plus 2, but then we multiplied both sides by 2. If we want to put it all together, we take the first equation, or the first inequality, added with the second inequality to get f of 0 plus f of 4 over 2 plus f of 2 is at least f of 1 plus f of 3 plus 4. And now we chain it with the last inequality that we have to get that this is greater than or equal to 2 times f of 2 plus 8. And now canceling the f of 2 from the from the leftmost side and the rightmost side, we will get f of 0 plus f of 4 over 2 is at least f of 2 plus 8. Aha! Our original inequality states a plus 4 there. So if we go back, we can see that what we expect is f of 0 plus f of 4 over 2 is at least f of 2 plus the absolute value of 0 minus 4, which is 4. But instead, we have a plus 8. So then the question is, can we continuously improve our inequality seemingly by a factor of 2 on the absolute value of x minus y? If so, we could get something that looks like f of 0 plus f of 4 is at least something that is arbitrarily large because we keep increasing this factor of 2. Now this would be really good for us because this is impossible. Since f of 0 and f of 4 are constants, they cannot be greater than or equal to something that can go arbitrarily large. And this would solve the problem. It turns out that we actually can't, because if we continuously use the new best inequality that we get, and we keep repeating the same process, we can end up with what we want. We can end up with an arbitrary factor on the absolute value of x minus y term. So let's turn this into a proof. So let's say suppose not. Then there exists a positive integer k such that, and then we just have our original inequality except with a k in front of the absolute value of x minus y. The reason why I can structure it like this is I'm basically saying k is the best that we can do. So k is kind of like the best factor that we can put in front of this absolute value of x minus y. And I know k can be a positive integer because I know k is at least 1 from the problem. So this holds for all reals x and y, but the other one is not true for every single x and y. So if I try to increase k by 1, it suddenly becomes false for some values of x and y. So let's say x and y are 4a and 4b for reals a and b. And I do this purely to avoid fractions on the f. Now you don't have to do this step. You can just continue to use x and y and just sub in the fractions, but I just did it like this so I can save some space. So we have f of 4a plus f of 2a plus 2b over 2 plus f of 2a plus 2b plus f of 4b over 2. And so the first term becomes this f of 3a plus b, and the second term becomes this f of a plus 3b, and the absolute values that come from these terms become the 4k times the absolute value of a minus b. And then we just chain the inequality to get f of 3a plus b plus f of a plus 3b is greater than or equal to 2 times f of 2a plus 2b. And again, we add on an absolute value of 4k times the absolute value of a minus b. And so this becomes 8k times the absolute value of a minus b. Thus, if we sub in the x and y's back, we will get f of x plus f of y over 2 plus f of x plus y over 2 is at least 2 times f of x plus y over 2 plus 2k times the absolute value of x minus y. And now canceling f of x plus y over 2 from both sides, we will get f of x plus f of y over 2 is at least f of x plus y over 2 plus 2k times the absolute value of x minus y. Recall that we said k was the best that we could do, and of course 2k is at least k plus 1, so it's better than what we said was the best, right? We said the best was k, but now we have a 2k, and of course 2k is bigger than k because k is a positive integer. Thus we are finished and we have proved the problem. So what did you think? Did you solve it before I showed you the solution? Do you have some other different way of doing it? Make sure to comment down below. Happy solving!